Welcome to the class. We had actually started discussion about psychrometry, where the major focus was towards the calculation of properties for humid air. There is a tool which is very much helpful for psychrometry, and it is called as psychrometric chart. Today's topic of discussion is psychrometric processes and psychrometric chart. So let us see. So first let us see psychrometric chart. This is basically a chart which has one y-axis, one x-axis, where this y-axis is the specific humidity, and x-axis is dry bulb temperature. X-axis for this chart is dry bulb temperature, and so this is T dry bulb. So this is specific humidity, this is dry bulb temperature, and then there are, like our PV chart, like our TS chart, this is also a chart with of omega versus TB, but this is little unusual, and here we can show different lines. So first line what we can show is this, and such lines are constant phi lines, in which phi is constant, relative humidity is constant. Then we can as well draw two lines. One is this kind of line which is having T wet bulb constant. So this is a constant wet bulb line, and constant wet bulb line can also be treated as constant enthalpy line, since they are almost parallel with each other. So this is H constant, and then there is one more line which is specific volume constant. So these are the different lines on this psychrometric chart. Now what we are going to see are the different processes on the psychrometric chart. We know, suppose we take TS diagram, then this line shows isothermal process, this line shows isentropic process, and then there would be one more line which is suppose like this, which is constant pressure process. So as what we show on TS diagram, similarly we can show different processes in the psychrometric chart. So psychrometric chart, let us talk about some processes. First process we are talking about is simple heating or cooling process. Suppose there is a duct, and in which this is a heater, so humid air is coming at state 1 and humid air is leaving at state 2, and suppose this is a heater, so in this case air will get heated, but we have to remember one point, that this air will have some omega 1 and some omega 2 at the outlet, and some phi 1 and some phi 2 at the outlet. Here omega 1 remains equal to omega 2, since specific humidity is not going to change in this process. This is as well true for the simple cooling process also, where this will be a cooler or cooling circuit. However, as we had already seen that heating would increase the temperature and hence the bearable capacity of the air for the vapor. So this will change the relative humidity at the outlet with respect to inlet. So this process of simple heating or cooling can be demonstrated like this on the chart by this. Suppose this is heating process and then this is cooling process. So by this we have to draw horizontal line For a given dry bulb temperature, we have to draw horizontal. From a given dry bulb temperature, we have to draw horizontal line at constant omega, and then accordingly we can get final state on that horizontal line for the simple heating or cooling process. Now, what is the amount of heat added or heat rejected? This Q is amount of heat interaction, that is equal to m dot A into H2 minus H1, where we know that m dot A is mass of air and H2 and H1 are the enthalpies per unit dry air's mass at the outlet and at the inlet. Having said this, we will see the next process, which is called as heating and humidification. The process is heating and humidification. In this process, we can have a heater, and this heater will first heat the air coming with certain dry bulb temperature, certain specific humidity, certain relative humidity, certain specific humidity. Then there will be some injection of water or steam after station 2 till station 3, and it comes out at state 3, where it will have phi 3, T3 and omega 3, and at station 2 it will have T2, phi 2 and omega 2. We can understand the process 1 to 2, or here is simple heating process, so we have omega 1 is equal to omega 2, but after that we are adding liquid, water or steam in the process 2 to 3 for humidification, then omega 2 is not equal to omega 3. So here this process can be shown on the chart, where we will have 1 to 2 is heating, and then 2 to 3 is humidification process, where we are increasing the omega. So this is what we have to keep in mind. Here we have to remember, if humidification is achieved by spraying steam, then T3 is greater than T2. If humidification is achieved by spraying cold water or water, then T3 can be less than water, then T3 can be less than T2. This is what we have to remember. So temperature here at this moment, this is state 3, we are saying that T3 is greater than T2, that means we are expecting the spraying of the steam is taken place in the process of humidification. If we are spraying liquid water, then water will evaporate, it will take the latent heat from the air, and in this case air would reduce its temperature. So T3 might be lesser than T2. Now we can have next process, which is cooling and dehumidification. And this process can again be shown in schematic way, where we will have some coolant passing in this circuit, and then we have state 1, we have state 2, and then there will be condensate, and that condensate will be taken out. So in this process we can see that if condensate is coming out, then this is dry bulb temperature, this is omega, and then we first will have decrement of the temperature 1 to x in this coolant, where phi is increasing in this direction, and then what would happen is at x we will reach phi is equal to 1, phi at x is equal to 1. Then condensation will start, and then we will reach state 2, where we would have lower temperature than state 1, and then we would have higher relative humidity after the removal of the condensate, where omega or specific humidity has decreased. So this is dehumidification. So we have reduced the specific humidity and we have reduced the temperature. There is fourth process, which is adiabatic mixing of air streams. Here in this process we can consider that there are two channels which are mixing and then forming one stream. So this is one, this is air at state 2, this is air at state 3. So state 1 has its own omega 1, phi 1, T1, H1. This will have omega 2, phi 2, H2, T2. And then we will have omega 3, H3, phi 3 and T3. Here we can remember that m dot A1 plus m dot A2 is equal to m dot A3. This is for air. Then for water vapor we will have omega 1 into m dot A1. This is specific humidity is mass of vapor per unit mass of dry air, so we have multiplied. So this is mass of vapor in state 1 plus mass of vapor in state 2 is equal to mass of vapor in state 3. So this is for vapor, and we will name it as equation 2, this as equation number 1, and both are mass conservation equations. Now we will write down energy conservation equation, where we will have H1 into m dot A1, this is specific enthalpy, which is enthalpy per unit mass of dry air, plus H2 into m dot A2 is equal to H3 into m dot A3. This is equation 3, and this is energy conservation. Let us take equation 1 and 2. So we can write down m dot A1 plus omega 2 into m dot A2 gives us m dot A3 into omega 3, which is equal to m dot A1 plus m dot A2 into omega 3, which is m dot A1 omega 3 plus m dot A2 omega 3. So we have omega 1 minus omega 2 minus omega 3, omega 2 minus omega 3 into m dot A2 is equal to omega 3 minus omega 1 into m dot A1. So we can write down m dot A1 upon m dot A2 is equal to omega 2 minus omega 3 divided by omega 3 minus omega 1. This we will name it as equation number 4. Now we will go ahead and write down the energy equation. Again consider 1 and 3. We can write down m dot A1 into H1 plus m dot A2 H2 is equal to m dot A3 H3. So we have m dot A1 H1 plus m dot A2 H2 gives us m dot A1 plus m dot A3 into H3. So m dot A1 H1 plus m dot A2 H2 is equal to m dot A1 H3 plus m dot A2 H3. So we can have m dot A2 again into H2 minus H3 is equal to m dot A1 into H3 minus H1. So we have m dot A1 divided by m dot A2 is equal to H2 minus H3 divided by H3 minus H1. So this is equation number 5. So we can write from 4 and 5 as m dot A1 divided by m dot A2 is equal to omega 2 minus omega 3 divided by omega 3 minus omega 1, which is also equal to H2 minus H3 divided by H3 minus H1. Now this is very simple to identify the states. State 3, if we know that we are at state 1 here, we are at state 2 here, then we have to identify where is our state 3, and that is why we would know mass flow rates m dot A1 and m dot A2. Then from m dot A1 and m dot A2 we can take their ratio. So this ratio is known to us. So left hand side is known to us. So we can draw a straight line between them, and then we can, since we know their ratio, we know this is omega axis and this is dry bulb axis. So for omega axis we can draw horizontal line from here. So here this ratio is known. So this is omega 2 minus omega 3 divided by omega 3. So suppose this is omega 3. So this is omega 2, this is omega 1. So this height over here is omega 2 minus omega 3, and this height over here is omega 3 minus omega 1. We will cut this horizontal, this straight line where we get this differences equal to, ratio of these differences equal to known left hand side, and then we can know the state 3. Similarly, we know constant enthalpy line is like this. So here as well we know enthalpy, which is H2, this is H3, this is H1. So this difference is H2 minus H3, and this difference is H3 minus H1. So we can again take the ratio of differences and find out the point where we will have that ratio is equal to known mass flow rate ratio, and thus we can identify the state 3. We need these informations and these processes, some of them for the necessary engineering application in the design of condenser or design of the parts of the condenser. Thank you.